This is topic 2.6, competing function model validation. In this video, we will explore patterns in data that reflect how linear, exponential, and quadratic models differ. I'm John Suttles from Lipscomb Academy in Nashville, Tennessee. So let's warm up. On the screen, you see three different graphs, and the equations of those three graphs are on the right side. Can you tell which graph goes with which function? If you need to, pause the video for a second and make your decisions. So maybe the first and easiest to identify is the line f of x equals x is the graph that has a constant slope. But between the other two, it might be a little bit more difficult to tell. If you said that the green graph was f of x equals 2 to the power of x minus 1, and the blue graph was f of x equals x squared, you are correct. So let's talk about how we could have identified that those were the correct graphs. But let's notice, first of all, that if we zoom out, the graphs look very different. On the left side of the screen, the graphs look very similar on the interval from x equals 0 to x equals 1. But if we were to expand our x values from, let's say, for example, negative 40 to positive 40, we can see much greater differences in the three types of graphs. So what can we tell from these comparisons? Well, first of all, like we looked at when x equals 0 and x equals 1, it was very difficult to tell those three graphs apart. But usually, if we have 3 points, we have enough information to assess which model is going to be best. Is the graph a quadratic model or an exponential model? The greatest differences in the graphs occurred when x was negative. But this may be rare in real-world settings. For example, if time is your independent variable, negative values may not be applicable. So we cannot rely on using negative x values as our distinguishing characteristics. So what then? When x was positive and greater than 1, the linear function began to look distinctly different from the other two. The rate of growth was constant, whereas the others were increasing at a faster rate as x increased. So thankfully, we do have a very clear way to determine the difference between a quadratic model and an exponential model, even though they look very similar. So what are the distinctive traits of each function? You may notice these graphs differ in shape, but can we be more specific? The rates of growth are the difference. That is, we'll talk about the rates of growth specifically as the change in y on equal interval changes in x. Linear models have a constant slope. That is, the y values increase by a consistent amount for equal intervals of x. These are like arithmetic sequences. Exponential models have y values that grow proportionally. For example, the points 4, 3, 5, 6, and 6, 12 are on a function, and notice that the y values are multiplied by 2 on each 1 unit increase in x. Therefore, that looks like an exponential model. Now, quadratic models have two distinctive qualities. First of all, unlike the other models, they can repeat y values. Remember on the shape of the quadratic graph, it turned around, right? It had more of a U shape. So that indicates that the y values can be repeated. And secondly, the differences between the differences of the y values are constant. So let's look at an example. What type of model is represented by the data shown on the screen? The first place we want to look is at the differences between the values of f of t. Now notice that the differences between the t values are consistently 2, and the differences between the f of t values are consistently negative 2.2. So for every 2 unit increase in t, the values of f of t consistently decrease by 2.2. So since those differences are constant, a linear model will be our best choice. Let's look at another example. Now, in this case, it's evident that the values of y are not changing by the same amount for every 1 unit change in x. So let's take a look at the ratios. For example, 2 divided by 0.5 is 4. So we had to multiply 0.5 by 4 to get to the next y value. And notice, to get to 8, we had to multiply the 2 by 4 as well. 8 divided by 2 is 4, and 32 divided by 8 is 4. So what does this mean? If the ratios are constant on equal interval widths of x, for every 1 unit difference in x, the y values are proportional. They're consistently multiplied by 4. So this indicates that an exponential model will be best. Let's look at one more. Notice in this case, the changes in x, the difference in x values are 2. But notice the y values. Do you notice anything that we've commented on previously in this video that's present in the y values? So do you notice the -1 appeared twice in the y values? So, as we indicated a minute ago, unlike the other models, quadratic models can repeat y values. So that alone suggests that a quadratic model is our best choice. What about this one? Much less clear when we look at the y values. However, it is evident that the differences are not constant. But what we're going to see here, if we look at the differences, is a difference of 15.1, 5.3, -4.5, and -14.3. If we were to find the ratios, we would also find the ratios are not constant. Our next step might be to look at the differences between those differences. From 15.1 to 5.3, we find a difference of -9.8. Likewise, from 5.3 to -4.5, we find a difference of -9.8. And likewise, with the last pair of y values. Remember, the second distinctive characteristic of a quadratic model was that the differences between the differences of the y values are constant. And that suggests the quadratic model will be our best option. So what should we take away? The primary question we answered was, how can we tell which type of model is best? And we talked about how we needed at least 3 points to effectively assess which model is best. We talked about how we notice y values that are repeated, a quadratic model will be best. If the differences are constant over equal intervals of x, a linear model will be best. And we also discussed if the differences between the differences in the y values are constant, a quadratic model will be best. And finally, are the proportions between y values over equal intervals of x constant? If so, if an exponential model will be best. Thank you very much.